Hello everyone, welcome back to my YouTube channel. Today we'll start this video with a topic using behavior modeling and writing the verilog code for JK flip-flops and different types of flip-flops. A deep dive into JK, SR, T and D flip-flops. This presentation will explore the design of various flip-flop types using behavior modeling in Verilog HTL from fundamental concepts to practical implementation. We will delve into the intricacies of JK, SR, T and D flip-flops, providing a comprehensive understanding of the behavior and applications. Introduction to digital logic circuits and flip-flops. Digital logic circuits are the foundation of digital systems employing binary signal 0 or 1 to perform operations like arithmetic, control, and memory. They use logic gates like AND, OR, NOT, XOR, etc. Flip-flops are the basic memory elements that store a single bit of data. They are crucial for building registers, counters, and other sequential circuits that involve storing and manipulating information over time. Fundamentals of Verilog HDL and Behavior Modeling. Verilog HDL is a hardware description language used to model and design digital circuits. It provides a textual way to represent hardware components and their behavior. Behavior modeling. Behavior modeling in Verilog describes how functionality of a circuit without specifying its exact implementation. It focuses on the input-output relationship and the circuit's behavior over time. Design of JK flip-flop using behavior modeling. JK flip-flop. A JK flip-flop is a versatile type that uses two inputs, J and K, to control its state transitions. It has a clock input and a reset input for synchronizing operations and resetting the flip-flop. Behavior model describes the behavior of a JK flip-flop by specifying the output, that is Q, based on the input signals and the current state. Verilog code for JK flip-flop with active low reset. First we have to give the module name JK flip-flop. Inside the bracket we have to give inputs and outputs. J and K are the inputs for the JK flip-flop. Clock signal for clock synchronization. Reset N is the active low reset signal. When low, it resets the flip-flop. Q is the output of the flip-flop, which declares as rich because it stores value in this sequential block. Always at the post edge clock. Uh, this block is triggered on the rising edge of the clock or the falling edge of reset N. This ensures that the flip-flop responded to the reset signal immediately regardless of the clock. If reset N is low or it is true, the output Q is reset to 0. If reset N is high, the JK flip-flop operates based on the values of J and K. The end module, it marked the end of the model definition. Design of SR flip-flop using behavior module. SR flip-flop, also known as the set reset flip-flop, uses two inputs S and R for setting and resetting its state. It has a clock input for synchronizing operations. Behavior module. The behavior module defines the output based on the input signals S and R and the current state of the flip-flop. It ensures proper behavior for different input combinations. Verilog code for SR flip-flop with active low reset. Again here we have to give the module name, inputs, outputs and a reach and always block, and then we have to end the module. Design of T flip-flop using D flip-flop. T flip-flop. A T flip-flop, also known as a toggle flip-flop, used a single input T to control its state. It toggles its output on each rising edge of the clock if T is high. D flip-flop implementation. A T flip-flop can be implemented using D flip-flop by connecting the T input to the D input and inverting the output Q before feeding it back to the D input. Verilog code for T flip-flop and using D flip-flop. Here also module name first we have to give, then inputs, outputs and reach, always block and end module. Design of D flip-flop using behavior modeling. D flip-flop is a fundamental flip-flop type that uses a single data input D to store a value. It has a clock input for synchronizing operations and a reset input. Behavior module. The behavior module describes the behavior of D flip-flop by defining the output Q to be equal to the value of the data input D on the rising edge of the clock. This ensures that the flip-flop latches the data input on the active clock edge.